So how do we carry out the analysis? Well, in the case of fixed effects analysis, it's pretty easy. A fixed effects analysis really is nothing but a concatenation of all the data. So imagine taking all the runs from every subject and just concatenating them all as if it were one giant run. Right? So take each of the participants' time series and just concatenate them one after the other, and then run a GLM. That is a fixed effects analysis. Again, because the only variance is the variance around the mean, so measurement error. And then, right, you run your GLM and you get some group analysis, which is a perfectly fine, as we said earlier, a perfectly fine analysis. Just what you can infer from it, right, might not be what you want. Now, if you think of this in terms of if you think of the matrix form, your y vector is the concatenation of the time series from all the participants. Then you have a group effect, which is really just the mean across all participants of the effect. And then there's some error term. But as I said, this is typically not what we want to do. We want to do something like a random or a mixed effects analysis. Now, how do we do that? Well, using a similar idea to what I'm showing here, you can do what is known as the all-in-one approach. And this would be the appropriate way of doing it. Now, the idea is that you do one giant GLM, which brings together in it all the data and tries to relate all the time series to both subject-specific and group-level parameters. Let me explain. So in this case, we would have y, which again, y is all the concatenated time series. But instead of only having one group effect, right, earlier all we had was an X matrix, which averaged the effect across every participant, and then the group effect. Here we have a longer expression, which within it has the effects at the single subject level. Let me explain. So Y, as I was saying, is the concatenated time series. Then we have X group. This is the second level design matrix. This is, what is the design at the high level? Is it, for example, patients versus controls? Or maybe, one effect is task A and the other one is task B, right? That's what we're talking about. Sort of how do we aggregate at the group level the data from the individual participants? Beta G, just like before, that's the group level parameter. That's the parameters we're trying to estimate. How big is the effect of something at the group level? So these are the group variables. Then we have the single subject variables. X is a matrix of all the single subjects. Bij is the vector, well, it's the parameters at the single subject level. And then there's an error term. Let me show you what I mean in a graphic way. So again, our dependent variable y is just that we concatenate all of the data. And then instead of having just sort of the 1, 1, 1, 1, 1, the average across, right, the average effect across everybody, what we do is this is our group level design, so XG. So again, this could be, right, healthy volunteer, patient, healthy volunteer, patient, healthy volunteer, patient. And so beta G1 could be the effect associated, the average effect associated in all the healthy volunteers. And beta G2 is the effect associated in all the patients. Or maybe, this is task A, looking at faces. This is task B, looking at houses. So beta G1 is what's the effect across my whole group of seeing faces, these. And beta G2 is what's the effect of seeing houses, something of that sort. And so these two are my group level parameters that I care about. Then there's X, which is the single subject matrix. So this is the matrix of participant 1. Maybe they saw a face, then a house, then a face, then a house, then a face, then a house. This is the matrix for participant 2, all the way to participant N. And these are here, they're called eta, but these are what we call the betas for each participant. So this is beta, for example, participant 1 for condition 1, which might be faces. This is the beta for participant 1, condition 2, which perhaps is houses. So these are the single subject effects. And then, of course, there's an error term. So see, this all-in-one strategy, you take the data, you concatenate it, and then you include in the regression both the individual level matrices, and the individual level betas, and the group level matrix, whatever it is that you're trying to do, and the group level parameters. And these are the parameters we care about. So this would be the proper way of doing this analysis. Now, the problem, of course, is that this is computationally massive. If you think of it, why, right? So the time series, I mean, we're talking about, some 100 TRs or some hundreds TRs for some 20 plus participants, although today even hundreds sometimes. I mean, the matrix inversion to be done here is huge and terrible. Computationally, it's extremely intensive. On top of it, if you think of it, say that now you collect one more participant. You have to redo the whole calculation all over again. So in the sense, it's a very inefficient way of doing the analysis. And that's why this is not what we typically do in fMRI. What we do in fMRI is something different. What we do in fMRI is what we refer to as the Summary Statistic Approach. And it goes as something like this. Let's take, this is our first level analysis, is what we did last week. So this is the time series for a voxel for run 1 of participant 1. This might be the matrix, maybe condition A, condition B, condition C. And these are the various parameters, each attached to one of these regressors. And then some error term. So we run our GLM, and it turns out we get some kind of result. These are the parameters we get. And then maybe what we cared about maybe was condition 3 versus condition 2. I don't know, something of that sort. Right? So we cared about this minus this. Maybe this was faces and this was houses or something like that. So we do faces minus houses. We do that and we get a number, 3 minus 56. So this particular voxel that we just analyzed cared minus 3.56 in this particular contrast. So here, instead of doing one giant analysis, what we do is we do the first level analysis, and then we take the results of the third level analysis and we carry those forwards. So we carry the beta or the contrast data, right? The contrast data. We carry that forward and into a group analysis. So in the second analysis, in the second level, or the so-called higher level analysis, what we're analyzing is the effect for this contrast in participant 1, then the effect for this contrast in participant 2, and the effect in participant 3, the effect in participant 4, etc. So what we do is we take the results from the first level analysis and then we aggregate those in a group analysis. And here we have some other type of grouping matrix, which could be, again, healthy volunteers versus patients, or this is just faces, the average of this, faces versus houses, or who knows. In this case, it looks to me like the example is really saying, for every participant, we create this contrast, we put it in, and then we want to compare the results from these participants versus these other participants, or at least we have two groups of participants. And that's why we have beta G1 and beta G2, which are our group level statistics. That's what we care about. And then, again, we estimate our two-level statistics. And maybe we want to know are healthy volunteers, do they have a, an effect different or bigger than than patients, something like that. And we do our little contrast, and we get this particular number, and that is the result of the group analysis. Right. So instead of doing one giant analysis, what we do is we do for every single run a first level analysis, and then we just take the results and aggregate those in a group level GLM. That's why we call this the summary statistic approach, because we run the first level, then we take a summary statistic, a summary result from the first level, and we carry that into the group level. So if this was our fixed effects analysis, our group effects analysis is something done with the summary statistic approach. Is something closer to this. You do the analysis of run one of this participant and you get a result. Then do the analysis of the run for this participant and you get a result. Do the analysis of the third participant and you get a result, et cetera, et cetera. And then you take these statistics here and you do the group analysis over these, and you get your group map. All right, so in fMRI, in order to avoid doing the giant all-in-one model, which is the correct one, but it's just too inefficient to carry out, we resort to this so-called summary statistic, or it's often known also as the hierarchical approach. Again, let me show this in a sort of a slightly different way. What we would do in the summary statistic or hierarchical approach, we do for every participant, we analyze, we run a GLM. And for example, in this participant, this is the magnitude of the effect, and this is their within subject variance. Participant 2, they had a big response, as you can see, so the magnitude of their effect is this green line, it's pretty big, so their beta is pretty big, and this is their sigma squared within. And subject 3 has a slightly smaller effect, et cetera, et cetera. So for every subject, we run a first level GLM, and for every voxel, we get a beta, an estimate of the effect, and an estimate of the variability within. Then we take this result across the whole brain, and we carry forward these betas into the second level. So we take the betas from the first level, and then we use those in the second level analysis. Again, the way we would do it is that we take these, we average, right, the effect across all the participants, and boom, here's the group level effect, right? The group level beta, or beta G. That's how big the effect is. And now, as always, we have to say, well, okay, what variance are we going to use? We could use the mixed effects variance, which is this one right here. We could use the between subjects variance or the within subjects variance. And if you think of it, the between subject variance is just if you take these effects here, you calculate the variance across them. That's your between subject variance. So this is how much variance there is across my participants in how big the effect is, how big their response is to whatever the task was. The within subjects effects, on the other hand, is really the average of all the within subject variances, which just happens to be in our depiction this much. So what is that? So this would be the random effects. This would be the fixed effects. And obviously the mixed effects is the sum of these two. This. So how big is the mixed effects analysis and the mixed effects variance? This much. And this makes a few things obvious. First, typically, well, first, the mixed effects variance is always larger, at most equal to either of these two, right? Because it's the sum, it's given by the sum of the two. Now, this also means that the mixed effects is typically always at most equal to these two, but typically larger. So mixed effects proves to be usually a much more conservative yardstick. So if you can meet that yardstick, then making an inference towards the population is more warranted. And so now what we could do, this is our effect. We could compare it to this yardstick here, the within subject variance. If we did that, this would be a fixed effects analysis. If instead we compared our average effect to this yardstick, that would be a random effects analysis. And if instead we compared our effect here to this yardstick, that would be a mixed effects analysis. And according to which of these we did, we can make a certain inference. In our case, we want to use the mixed effects analysis, the mixed effects variance, excuse me. So we will compare this against that. And, and obviously we would do this numerically, not visually, and we would get, for the whole brain, we would get some kind of map and some kind of statistical value. All right, but this is the idea in the summary statistic approach. You run a first level analysis for each participant, you carry forward the data, you calculate the variance across participants, then you average the variance within each participant, and that's how you get your between variance and your within variance, or your random effects variance and your fixed effects variance. And then you choose which variance, which yardstick you want to use. But be mindful, according to what yardstick you use, there are differences in what you can say. In fact, there are even differences in the validity of the various yardsticks, which I'll get to in just a second.